This is a video for AQA Discrete Mathematics, Binary Operations, section 2.4, which is looking at the idea of generators of groups. We've seen in previous videos how we define the order of an element as being the smallest value of n such that a to the power n is equal to e, where e, of course, is the identity. And we're using that notation a to the n to mean that we're repeating the operation with a n times. If there's no such value of n, then we talk about the element as having infinite order. By a generator of a group, we are talking about an element that, as we repeat those operations, produces each of the elements in the group in turn. So every single element can be here, the 1, 2, 3, 4, 5 and 6 can be produced by repeated operations of some of, but not necessarily all of, the elements. And so what we're asked to do here is to find which of the elements are in fact group generators. So, well, let's start off and see what happens. We can look at 2 and see what happens if we look at 2 squared. Remember, we're looking at multiplication modulo 7, so 2 squared is 4. 2 cubed will then be equal to 4 multiplied by 2, and that's 8, which modulo 7 is 1, but 1 is equal to e, so we can see that we've generated just the elements 4 and 1 from 2, so that's not a group generator. If, on the other hand, we look at 3, 3 squared is equal to 9, which modulo 7 is 2. Then 3 cubed must be 2 multiplied by 3, which is 6. 3 to the power 4 will be 6 multiplied by 3, which is 18, and modulo 7, that is equal to 4. So that 3 to the power 5 will be 4 multiplied by 3, which is 12, which is then modulo 7 is 5. And 3 to the power 6 will be 5 multiplied by 3, which is 15, which is 1, which is the identity element. So you can see that 3 is order 6, and it's produced all of the other elements, 1, 2, 3 itself, of course, 4, 5 and 6. So therefore we can say that 3 is a group generator. Notice that the order of 3 is 6, which is equal to the order of the group. It's easy to check that 5 is also a generator. And this is going to be true because if you look at 3 multiplied by 5, then that is equal to 1, which is the identity element. So 3 and 5 are inverses of each other. And you can also check that for 4 and 6, these are not generators. So for example, 6 is only order 2 because 6 squared is 36, which is equal to 1 modulo 7. And 4 is also modulo 3, being the inverse of 1, which we can see, the inverse of 2 rather, which we can see in that calculation there. So 3 and 5 are the group generators for this particular group. Groups that are generated in this way by a single element are also known as cyclic groups, and we can see this idea in this set of multiplications here, where we started off with 3 to the power 1, of course, being equal to 3, and then it will cycle round again once we get to the end. 3 to the power 6 is 1, and then we get to 3 going on from there. So every element 3, 2, 6, 4, 5, 1, and then it will repeat. So you have a cycle of elements being produced. So a cyclic group is one where we're generating the whole group by a single element. And cyclic groups are often written in this form. So we've got the element there written in this bracket together with the binary operation. So for example, the cyclic group that we were talking about could be written as being the group which was 3 and then the operation multiplication modulo 7. Or of course we could write it as 5 modulo 7 because 3 and 5 are both generators of the whole group. Well, here's another cyclic group which is produced by the Cayley table, and we want to find a generator for this one. We can see that A is the identity element. If you look here, we've got clearly A is the identity, and so we can therefore check the order of each of the elements. Well, B is order 2, because B squared is equal to E, and therefore that's not going to be a generator. And therefore we're left with C or D. So let's check C. Well, C squared, that is equal to B. So C cubed will be equal to B combined with C. If we check that, we get D. C to the power 4 will therefore be D combined with C, and if we check that one, we get A. So there we've got all of the elements, C itself, B, D and A. And notice again that the order of C is power 4, which is the order of the group. So we can say that C is a generator, and indeed you could do the same thing for D. And notice again that D and C are inverses of each other. This time we're asked to determine the order of the group given the fact that it's a cyclic group where 2 is the generator and we're looking at addition modulo 5. So this is a case of just going through then. Obviously 2 to the power 1 is 2. 2 squared will be 2 plus 2, which is 4. 2 cubed must be then 4 plus 2, which is 6, and that's equal to 1 modulo 5. Now remember that 1 is the identity for multiplication mod 5, but we're looking for E in this case to be 0, which is the identity for addition. So we carry on. 2 to the power 4 is equal to 1 plus 2, which is 3, and then finally 2 to the power 5 is equal to 3 plus 2, which is 5, which is modulo 5 is equal to 0, and that's equal to the identity element. So the order of the element is 5, and therefore the order of the group is 5. There are 5 elements, and we could write them as 0, 1, 2, 3, and 4. That's the end of this video looking at generators and cyclic groups. In the next video we'll be looking at the idea of subgroups.